The Millennium problem you're referring to is commonly known as the PVS-NP problem, which is one of the 7 Millennium Prize problems selected by the Clay Mathematics Institute in 2000. These problems are considered to be some of the most difficult and important open problems in mathematics, each carrying a prize of $1 million for a correct solution. 1. PVS-NP is a question in theoretical computer science that deals with the efficiency of problem solving using computers. It asks whether every problem whose solution can be quickly verified by a computer can also be quickly solved by a computer too. Here's a deeper look into the concepts. P. Polynomial time. P stands for polynomial time, which refers to the class of problems that can be solved quickly, in polynomial time, by a deterministic Turing machine. A deterministic Turing machine is a theoretical model of computation that formalizes the concept of an algorithm. Problems in P are those where we can find a solution in a time that grows polynomially with the size of the input. For example, if we have an algorithm that sorts a list of numbers, and it takes time proportional to the square of the number of items in the list, n2, this problem is in P. NP, non-deterministic polynomial time. NP stands for non-deterministic polynomial time. It includes all problems for which a given solution can be verified in polynomial time. This doesn't necessarily mean we can find a solution quickly, it just means that if we're given a potential solution, we can check its correctness quickly. A classic example of an NP problem is the Hamiltonian path problem. Given a list of cities and the distances between them, the task is to find a path that visits each city exactly once and returns to the origin city. If someone gives you a path, you can quickly check if it meets the criteria, but finding that path from scratch is much harder. PVS-NP question. The PVS-NP question asks, if it's easy to check that a solution to a problem is correct, NP, does it mean it's also easy to find the solution, P? In other words, is P equal to NP? This question is fundamental because if P were equal to NP, it would mean that all problems that we can verify quickly, we could also solve quickly. This would have profound implications for mathematics, computer science, cryptography, algorithm design, and many other fields. Why it's a Millennium problem? The PVS-NP problem is unresolved. No one has been able to prove whether P is equal to NP or not. It's a Millennium problem because solving it would advance our understanding of computational theory and the limits of what we can compute. The difficulty lies in proving that no possible algorithm could solve NP problems quickly, which is a very different challenge than just not having found a fast algorithm yet. In summary, the PVS-NP problem is a fundamental question about the nature of computational problems and their solutions. It asks whether problems that are verifiable in polynomial time are also solvable in polynomial time. The implications of this problem are vast, and solving it would represent one of the most significant breakthroughs in the history of mathematics and computer science. Cryptography is deeply intertwined with the PVS-NP problem, as the security of many cryptographic systems relies on certain problems being hard to solve, which is to say, not solvable in polynomial time by any known algorithm. Here's a detailed explanation: cryptographic systems and hard problems. Cryptographic algorithms, like RSA, depend on the assumption that certain mathematical problems are hard to solve. For RSA, the hard problem is factoring large prime numbers. The security of RSA keys, for example, is based on the difficulty of factoring the product of two large prime numbers 1. If P equals NP, it would mean that problems that are currently considered hard, like factoring large primes, could potentially be solved quickly, in polynomial time, which would undermine the security of these cryptographic systems. Implications of P equals NP for cryptography. If it were proven that P equals NP, most current cryptographic algorithms considered secure could become vulnerable. 1. This is because the encryption and decryption processes in cryptography often rely on NP problems. For instance, breaking RSA encryption is currently considered an NP problem. If P equals NP, then breaking RSA encryption would become a P problem, meaning it could be done quickly and efficiently, rendering the encryption insecure. 1. Current state and future of cryptography. As of now, no one has proven P equals NP or P not equal to NP. Cryptographic systems are designed with the assumption that P not equal to NP, meaning that the problems they rely on are too complex to solve quickly. If P equals NP were proven, we would need to find new cryptographic systems that do not rely on the hardness of NP problems. This might involve using larger key sizes or entirely different algorithms that are secure even if P equals NP1. Conclusion: the relationship between cryptography and the PVS-NP problem is fundamental. The security of many cryptographic systems hinges on the belief that P not equal to NP. A proof either way would have a significant impact on the field of cryptography, potentially requiring a complete overhaul of current encryption methods to maintain data security. Quantum computing has the potential to significantly impact the relationship between cryptography and the PVS-NP problem. Here's a detailed explanation of how quantum computing and cryptography. Quantum computers operate on principles of quantum mechanics, which allow them to perform certain calculations much faster than classical computers. 2 quantum algorithms, in particular, have significant implications for cryptography. Schia's algorithm. This algorithm can factor large prime numbers efficiently, which could break the RSA encryption system, an NP problem that relies on the difficulty of factoring 1. Grover's algorithm. While not as powerful as Schia's, Grover's algorithm can speed up the search for a solution to an unsorted database, effectively squaring the speed of brute force attacks on cryptographic hash. 1. Impact on PVS-NP. Quantum computing does not directly solve the PVS-NP problem, but it does change the landscape of what is considered computationally feasible. If quantum computers become practical, they could solve problems that are currently in NP, like integer factorization, in polynomial time, which classical computers cannot do efficiently. However, this does not mean that P equals NP, as the PVS-NP problem is defined within the realm of classical computation. Quantum computation introduces a new class of complexity, often denoted as BQP, bounded error quantum polynomial time, which is not directly comparable to P or NP. Post-quantum cryptography. In anticipation of quantum computing becoming a reality, researchers are developing post-quantum cryptographic algorithms that are secure against both quantum and classical computers. 1. These include lattice-based cryptography, multivariate-based cryptography, hash-based signatures, and code-based cryptography, which are believed to be resistant to attacks by quantum computers. 1. Conclusion. Quantum computing challenges the current assumptions of cryptographic security based on NP problems. While it does not answer the PVS-NP question, it necessitates the development of new cryptographic systems that can withstand the power of quantum algorithms. The field of post-quantum cryptography is actively researching these solutions to ensure data security in a future where quantum computing is prevalent. Post-quantum cryptographic algorithms are designed to be secure against the potential future threats posed by quantum computers. Here are some examples of these algorithms. Lattice-based cryptography. Crystal's Kyber, a key encapsulation mechanism that is based on the hardness of solving problems in structured lattices. 1. NTRU, an encryption algorithm that is also based on the hardness of lattice problems and has been studied for many years without any feasible attacks being found. 2. Hash-based cryptography. Sphinx Plus, a stateless hash-based signature scheme that provides security based on the well-understood hardness of hash functions. 1. Code-based cryptography. Michaelis cryptosystem, based on the hardness of decoding a general linear code, which is considered to be resistant to quantum attacks. 2. Multivariate polynomial cryptography. Algorithms based on the difficulty of solving systems of multivariate quadratic equations over finite fields. 2. Isogeny-based cryptography. Cryptographic schemes that rely on the difficulty of finding isogenies between elliptic curves. 2. These algorithms are part of ongoing research and standardization efforts to develop cryptographic systems that can withstand the capabilities of quantum computers. The National Institute of Standards and Technology (NIST) has been leading a process to evaluate and standardize post-quantum cryptographic algorithms, and some of the mentioned algorithms are among those being considered for standardization. Digital signatures, algorithms like Crystal's Dilithium, Falcon, and Sphinx Plus are being tested for their performance in digital signature applications, which are crucial for verifying data privacy, authenticating documents, and ensuring the integrity of communications. 1. 5G/6G services. Post-quantum cryptography is being analyzed for its potential to secure next-generation wireless networks. Performance analysis of these algorithms is essential to select secure and efficient ciphers for specific services in these advanced networks. 1. Web applications. The use of post-quantum cryptography in real-time encryption for web applications has been mentioned, with a focus on the impact on time efficiency compared to classical cryptographic algorithms. 2. Financial transactions. These algorithms are also used to protect private transactions, such as debit and credit card purchases, ensuring that these transactions remain secure against potential quantum computing threats. 3. As quantum computing advances, the adoption of post-quantum cryptographic algorithms will likely increase, with more practical applications emerging across various sectors to ensure data security and privacy in a post-quantum world. The Millennium problem PVS-NP, if solved, could have profound and far-reaching applications in various fields. Here's a detailed exploration of the potential applications, optimization and scheduling. Efficient resource allocation. Solutions to the PVS-NP problem could lead to algorithms that can quickly solve complex optimization problems, such as scheduling flights, allocating resources, or routing deliveries with optimal efficiency. 1. Improved manufacturing. Manufacturing processes that require complex scheduling of machinery and workflows could be optimized, leading to significant cost savings and productivity gains. 1. Computer science and algorithm design. Algorithmic efficiency. A positive resolution, P equals NP, would mean that algorithms could be designed to solve NP problems efficiently, revolutionizing fields like database search, pattern recognition, and artificial intelligence. 1. Software development. Software verification, which ensures that programs perform as intended, could become more efficient, making software more reliable and secure. 1. Cryptography. Cryptanalysis. If P equals NP, then cryptographic systems that rely on the hardness of NP problems could be broken efficiently, necessitating a complete rethinking of digital security protocols. 2. Secure communication. Conversely, if P not equal to NP, it would affirm the security of many cryptographic systems, providing a solid foundation for secure communication and data encryption. 2. Science and medicine. Drug discovery. The ability to solve NP problems efficiently would enhance the speed and accuracy of molecular simulations, potentially accelerating the discovery of new drugs. 1. Genome analysis. Bioinformatics could benefit from efficient algorithms for analyzing genetic data, leading to breakthroughs in understanding diseases and developing treatments. 1. Economics and game theory. Market analysis. Economists could use efficient algorithms to solve complex market equilibrium problems, improving predictions and strategies for markets. 1. Strategic decision-making. Game theory problems, which often fall into the NP category, could be solved more efficiently, aiding in strategic decision-making for businesses and governments. 1. Mathematics and theoretical research. Mathematical proofs. A solution to PVS-NP could provide new methods for automated theorem proving, potentially solving long-standing mathematical conjectures. 1. Complexity theory. The field of complexity theory itself would be revolutionized, as the relationship between different complexity classes would be better understood. 1. In essence, the PVS-NP problem touches on the core of computational complexity and has implications for virtually every field that relies on computing and problem solving. The potential applications are vast and could lead to a new era of technological and scientific advancement. However, it's important to note that these applications hinge on the theoretical resolution of the problem, which remains one of the most challenging and significant open questions in mathematics and computer science. The PVS-NP problem was formulated by American computer scientist Stephen Cook and independently by Soviet mathematician Leonid Levy in 197112. The problem was first introduced to the world by Stephen Cook in his seminal paper, The Complexity of Theorem Proving Procedures, presented at the 3rd Annual ACM Symposium on Theory of Computing. 3. Stephen Cook. Stephen Cook is considered the father of the PVS-NP problem. He was the first to formally define the problem and to introduce the concept of NP completeness. 1. Cook's work laid the foundation for the field of computational complexity theory, which studies the inherent difficulty of computational problems and the resources needed to solve them. Leonid Levy. Leonid Levy came to similar conclusions independently around the same time in the Soviet Union. His work paralleled Cook's, and he developed a theory that also defined NP completeness. 2. Levin's contribution is often recognized in the form of the Cook-Levy theorem, which states that the Boolean satisfiability problem, SAT, is NP complete. The Millennium Prize. The PVS-NP problem was later chosen as one of the 7 Millennium Prize problems by the Clay Mathematics Institute in 2004. These problems were selected because they are some of the most challenging and important unsolved problems in mathematics and carry a prize of $1 million for a correct solution. The formulation of the PVS-NP problem has had a profound impact on computer science, mathematics, and related fields, as it questions the limits of what can be computed efficiently. It remains one of the most significant open questions in theoretical computer science. The PVS-NP problem has had a profound influence on both algorithm design and complexity theory. Here's a detailed look at its influence on algorithm design. Heuristic algorithms. Since many NP problems cannot be solved efficiently, algorithm designers have developed heuristic methods that provide good enough solutions within a reasonable time frame. 1. Approximation algorithms. For problems where exact solutions are hard to find, approximation algorithms are designed to find near-optimal solutions quickly. 1. Worst-case analysis. Algorithm designers often focus on the worst-case scenario, which is influenced by the PVS-NP problem, to ensure that algorithms perform adequately under all conditions. 1. Influence on complexity theory. NP completeness. The concept of NP completeness, which emerged from the PVS-NP problem, has become a central idea in complexity theory. It helps in classifying problems based on their computational hardness. 2. Computational hardness assumptions. The PVS-NP problem has led to the development of hardness assumptions that underpin cryptographic protocols and security systems. 1. Resource-bounded computation. Complexity theory now includes the study of resource-bounded computation, such as time and space, which is directly related to the PVS-NP problem. 2. Interdisciplinary impact. Cryptography. The PVS-NP problem has influenced the design of cryptographic systems that rely on the hardness of NP problems for security. 1. Mathematical logic. In mathematical logic, the PVS-NP problem has motivated the search for proof techniques that can handle the complexity of NP-complete problems. 2. Thermodynamics and information theory. Recent interdisciplinary approaches have integrated concepts from thermodynamics and information theory to explore the PVS-NP problem, offering new perspectives on computational complexity. 3. The PVS-NP problem has not only shaped the way we think about algorithms and computational complexity but also has driven innovation across various fields, pushing the boundaries of what we understand about computation and problem solving. Researchers approach the PVS-NP problem using a variety of strategies, often drawing from different fields and theoretical frameworks. Here's a detailed look at some of the current research approaches. Interdisciplinary approaches. Thermodynamics and information theory. Some researchers are exploring the PVS-NP problem through the lens of thermodynamics and information theory. They focus on entropy and its relationship to computational complexity, proposing methods like entropy-driven annealing (EDA) to explore the energy landscapes of computational problems. 1. Mathematical logic and reducibility. Logical formulas. Complexity classes. Another approach involves investigating the satisfiability of logical formulas. Researchers look at EXP-complete languages and their reducibility to NP languages, aiming to demonstrate that if an EXP-complete language can be reduced to NP in polynomial time, then EXP equals NP. This would imply P not equal to NP, given that P not equal to EXP is already established. 2. Computational paradigms. Quantum computation. Some approaches involve the use of quantum computation paradigms to solve NP-complete problems. Researchers develop methods for solving problems through graph embodiment on a quantum computational paradigm, which could provide insights into the PVS-NP problem. 3. Algorithmic theory. NP-complete problems. A common approach is to focus on NP-complete problems, which are the hardest problems in NP. If any NP-complete problem can be shown to be solvable in polynomial time, then P equals NP. Researchers try to find efficient algorithms for these problems or prove that no such algorithms exist. Computational complexity theory. Complexity classes. Researchers also study various complexity classes and their relationships. They aim to understand the boundaries of these classes and whether problems in one class can be transformed into problems in another class in polynomial time. Cryptography. Cryptographic assumptions. Since many cryptographic systems rely on the hardness of NP problems, researchers in cryptography closely follow and contribute to the PVS-NP research, as any progress could have direct implications for the security of cryptographic protocols. Heuristics and approximation. Practical algorithms. While not directly solving PVS-NP, researchers develop heuristic and approximation algorithms for NP problems, which can sometimes offer practical solutions even without a theoretical breakthrough. The PVS-NP problem is one of the most challenging and significant problems in mathematics and computer science. Researchers from various disciplines continue to explore this problem, contributing new ideas and methods in the hope of finding a solution. The problem's resolution would not only be a monumental theoretical achievement but would also have practical implications across multiple fields. Recent progress in PVS-NP research has been more about advancing our understanding of computational complexity and developing new techniques to tackle NP-hard problems, rather than making direct strides towards solving the PVS-NP problem itself. Here are some key developments. Advances in algorithms and hardware. There have been significant improvements in algorithms and hardware that allow us to tackle many NP-complete problems more effectively than before. These advances have not solved the PVS-NP problem but have made it possible to address many practical NP-hard problems. 1. Machine learning and optimization. The growth of machine learning and optimization techniques has provided new tools to approach NP-hard problems, offering efficient solutions in some cases that were once thought impossible. 1. Graph isomorphism breakthrough. In 2015, Laszlo Babai, a Gödel and Knuth Prize winner, found a quasi-polynomial time algorithm for the graph isomorphism problem. This development opened up the possibility of proving NP equals QP, which is a significant step in understanding the complexity of certain problems too. Theoretical insights. There have been new theoretical computer science results that, while not directly solving the PVS-NP question, have provided valuable insights into the nature of computational challenges and the future possibilities for the field. 1. It's important to note that the PVS-NP problem remains unsolved, and these developments represent progress in related areas of computational complexity rather than a direct solution to the problem. The quest to resolve PVS-NP continues to be one of the most challenging and intriguing pursuits in computer science and mathematics. While the PVS-NP problem remains unsolved, there have been recent breakthroughs in tackling specific NP-complete problems. These advancements often involve new algorithms, heuristics, or computational techniques that improve our ability to find solutions or approximations for these complex problems. Here are some notable examples. Graph theory problems. Advances in algorithms and hardware have allowed researchers to tackle many NP-complete problems in graph theory, such as the maximum clique, vertex cover, and graph coloring problems. New heuristic and approximation strategies have been developed to find near-optimal solutions with minimal computational time and space complexity. 1. Optimization problems. The growth of machine learning and optimization techniques has provided new tools to approach NP-hard optimization problems, offering efficient solutions in some cases that were once thought impossible. 2. Graph isomorphism. A significant breakthrough was made by Laszlo Babai in 2015 when he found a quasi-polynomial time algorithm for the graph isomorphism problem. This development has implications for the complexity of certain problems and could provide insights into the PVS-NP problem too. Evolutionary methods. Recent trends in solving NP problems have included the use of evolutionary methods, which apply soft computing strategies to find solutions for classical NP problems like the traveling salesman and 0 to 1 knapsack problems. 1. These breakthroughs represent progress in related areas of computational complexity and demonstrate the ongoing efforts of researchers to develop new methods for solving or approximating NP-complete problems. The advancements contribute to our understanding of computational complexity and open up new possibilities for practical applications. That was all. Goodbye.